Good afternoon everyone, and today I am going to talk about the exactly solvable spin liquids in Kitaev bilayers and moiré superlattices. So you have already heard a lot about PO, 2D and 3D. Now it is completely bilayer. So just a very brief introduction. So when I am talking about spin liquids, so definitely something is solid and something is gas, and in that context I can tell that the magnet is kind of spin solids and the paramagnet is kind of spin gas, and spin liquid lies in between them, which is kind of a magnetic liquid where there is no order parameter exist, but some correlations between the spins are present. And in this context, in general, the interacting spin problems are very difficult to solve because of its numerical computational limitations. But if we can solve it exactly, then it gives us a very beautiful analytical insights what is happening within. And in this regard, Kitaev model is very successful. So if you compare the two models in the right hand side and left hand side, you can see that in the Hamiltonian, in the left hand side, the Kitaev Hamiltonian is bond dependent. So there are three coordination number is 3, and along with the 3 bonds, we can associate 3 different spin interactions by Pauli matrices. And if we do this, then Kitaev showed that we can decompose the spin in terms of the Majorana fermions, and this can be solved exactly by a beautiful reduced Majorana hopping problems where Uij is a very special operator. Which kind of operator is it? You can see that U square equals to 1. That means along each and every link, the U can take only 2 values, plus and minus 1. This is called a link operator, and this also commutes with the Hamiltonian. That means it is a conserved quantity. So this we call about the Z2 gauge field. However, this is not a gauge invariant quantity, but we can define some gauge invariant quantity from here, which is the plaquette operator, which is the multiplication of all the Uij's through over the plaquettes. Hence, so this also is a conserved quantity of the Hamiltonian. So if we can identify for which plaquette values throughout the lattices my system has the ground state, then I am done. And in this regard, for the Kitaev model, it shows that for all the plaquettes, the plaquette values are 1. That means it is a flux-free ground state. So a conventional choice is taking all the link operators to be 1, and then it is a very easy problem which can be solved exactly by the simple Majorana hopping problems. Now our motivation is little bigger. We want similar models but in the bilayer regime. But now there is a problem. The problem is now I have 4 bonds. So my coordination number is 4. So I need to incorporate the higher dimensional algebra here, and in this regard I can associate 4 gamma matrices instead of the Pauli matrix. So this is a 4 cross 4 matrix. First 3 is the gamma 1, gamma 2, gamma 3, and the interlayer bond is at gamma 4. So you can think of this is kind of a spin and orbital, both degrees of freedom are present within the systems, or also you can think of the spin multiple operators. And if we use the similar algebra as Kitaev did, we can see again we can decompose the same Hamiltonian in a very beautiful exactly solvable models. However, there are 2 Majorana fermions now present within the systems, which starts talking with each other in presence of an external magnetic field, and even then it is an exactly solvable model. So again we need to define our plaquette operators. There are 2 types of plaquette operator. One is the intralayer plaquette and another is the interlayer plaquette, square plaquette and the honeycomb plaquette. And the plaquette operator is defined as the link operators multiplication throughout the lattices. And if we do this, we get a very beautiful phase diagram of the flux crystals, where by changing the interlayer coupling strength and the external field, we can get different flux crystals. So the first index is my interlayer index, that is a 0, and the second index is my interlayer index. So what this implies, so the first, if you see the last, the two-third phase, then you can see that the first 2/3 means that 2/3 of my honeycomb is in the -1 phase, and for the second 2/3 of my square interlayer plaquettes are in the pi flux phase. So, and you can also see that a different gapped and gapless phases emerges within the systems, also with the quadratic band touching. Now again we are interested in more exotic situations. We have seen that this is a 0 pi sector, and now what if how this 0 pi phase evolves if we twist these bilayers. Now if we twist these bilayers, the interlayer is still now same, but interlayer will change. And how it will change? So now at each and every side the interlayer bond distance will vary, and as the interlayer bond distance will vary, so we can see that as the bond length increases, the coupling strength decreases, and we proved it by the exponential functions where r is the lateral shift. But along with this, I also introduced a cutoff on this, and you can see that if we why I have introduced this cutoff, because for my interlayer bonds, you can see that two situations, the blue is the bottom and the above is the top. You can see can be certain cases where the bottom and top may be connected by two interlayer bonds, but that is the problem. We always want that every side should have at most one interlayer bonds similar to the bilayers, and so we have imposed this cutoff and neglected all the weaker couplings from this bilayer. And if we do this, then our model is exactly solvable, and if we impose this constant in the Monte Carlo, we can see very beautiful phase diagrams. And this is a very beautiful in the sense because this is a general phase diagram, because all the plaquette patterns, they remain same regardless of the twist angles and twist centers throughout the twisted regime. And it turns out there are two different regimes. The corner is the blue regions and the middle one is the yellow regions. So this yellow is the AB stacking regions and the corner is the blue stacking regions, and we can see that for the A stacking region all the square plaquettes are -1, and AB this is +1, and there are also some odd-sided plaquettes, half of them are +I and half of them are -I. You can see for certain twist angles the pattern remains same for a particular twist center, and also if we change the twist center, still now my pattern is same. And also I am breaking the time difference symmetry, and so I am also getting some edge and corner localization, which is giving me a very beautiful patterns, and we can see different gapped and gapless spin liquid phases. So that is the summary. So we can see that this is a very tunable model we have proposed, and for the first ever exactly solvable bilayer models, where you can see different gapped and gapless spin liquid phase, and also edge and corner modes appear, and we can see that generalized patterns of the ground state regardless of the twist angle, twist center. So I want to thank my collaborators, and this is published in peer review. Thank you.